So this one's actually one that's worth recording. All right. So a lot of you are familiar with Ohm's law, and you have the symbol of a resistor, the symbol of a capacitor, and the symbol of an inductor. And the thing about Ohm's law is that all three of these devices it'll work for. All right, and so we can have a current through the resistor, a current through the capacitor, and a current through the inductor. And when you have a current passing through something, especially a passive device, you have a voltage drop across that device. Now, you're all probably familiar with resistance, and that VR equals IR through the resistor times the resistance. And that's because the impedance of the resistor is in fact the resistance. Now, you can do the same thing for capacitors and inductors, but the impedance is a different equation. And we have a couple of things here. C is just the value of the capacitor in farads, but S equals J omega. Quick review, J equals I equals square root of -1. Electrical engineering, we don't use I because many times that's current. And this happens to be the frequency of a sine wave in radians. Okay. So when you start talking about a capacitance, you're talking about frequency, because if the frequency was 0, this impedance would go to infinity. All right. ZL, S times L, where that's in henries, and that's still our J omega. So in order to know the value of this, you do have to know the frequency you're at. But ultimately, it's in ohms, and this would be in minus whatever you calculated it to be, J ohms, right? And then this would be positive, whatever you calculated it to be, ohms. All right. So once you have that, right, you don't have to worry about special rules about combining things in series and in parallel. So if I have a network here, right, RCL, right, you probably remember that if I have these resistors in series, I can turn that into an equivalent circuit, R1 plus R2 plus R3. Well, these elements are in series as well, and it can be turned into an equivalent element, but it's really ZR plus ZC plus ZL. And just as an example, right, I could just have 50 ohms minus 50 J ohms plus 100 J ohms. So it combines, except now we just have to deal with the complex math, right? And then what's a little harder for people to remember, even myself, is parallel, right? And that equivalent is 1 over R1 plus 1 over R2. Well, if I have the same thing, okay, good question. Thanks, Luca. Omega, the units of omega are in radians per second. And so when you have omega times a farad, you're going to get ohms. Nope. No. When you have 1 over omega c, you get ohms. And when you have omega L, you get ohms. But this is in radians, not hertz. Good question. So we have some elements in parallel here. The equivalent is just 1 over ZR plus 1 over ZL plus 1 over ZC, which it does involve complex math, but it's a lot easier than dealing with the differential equations. And the only thing you need to know is the frequency of which you're operating at, and then you can get numerical values. But a lot of times we just leave S as S, and we look at how the relationship with frequency between these elements interacts, rather than finding some specific thing. So, quick review. Series, right? So if I have B and A, doesn't matter how it's supplied, but I want to go from A to B, and I'm just, I'm current, and I flow through the first resistor. Can I go any other direction to get to B? Nope, I have to keep going through that next resistor. Is there another path to B? No, I have to keep going and keep going and keep going. And there's only one path from A to B, and so all these elements are in series, right? Now what about parallel? Right? I start at A, and I have a choice of 3 ways to go. I have a choice of 3 ways to go. I can go through this resistor and get there. I can go through this resistor and get there. I can go through that resistor and get there. So these are all in parallel, which we generally just put as these double L's here, right? So if I write R1 in parallel with R2 in parallel with R3, that's a shorthand that we use, all right? So if you see a series connection, right, you just sum them up, right? Or we could use impedances, Z1, Z2, Z3, all the way up. And if they're in parallel, right, you have 1 over, I'll do this in impedance, Z1 plus 1 over Z2 plus ... 1 over Zn, all right? And so what we can do is, sometimes we want to simplify a circuit, right, was that we can come up with a value for all of these, R equivalent, and then we just replace that with, our series, and this. Okay. Now when we do impedance, sometimes you'll see people just draw a box like that. Rather than drawing the L, R, or C symbol, they just draw a box. And sometimes I think you'll see it like that. All right. Now, we have a voltage supply. We have a resistance. We have two resistances here. And we'll label them. Now, if you're trying to identify, just looking at this circuit, what's in series and what's in parallel, well, that really means, you know, kind of the raw device. Now, some of you probably already know that R1 is in series with this equivalency, but R1 is not in series with R2 and R3 because the rest of these resistances would impact it. So the things that are in series without transformation, right, are R1 and R2. I mean, R2 and R3. Now, what's in parallel? Well, yeah, you probably can see that there's a parallel branch and a parallel branch here, but these guys are they're in parallel on their own, right? So if I were to ask you which branches are in parallel, you're coming along, you don't have a choice as current. Then you get to this node, and your current has a choice to go this way to get to the same spot, or it has a choice to go this way, and then it has another choice, right? But these two branches, right? So what one can do, and I'm going to go over this a little bit quickly because I show it in the notes, is that I can transform this circuit, right, like this. Okay, so now rather than have two resistors, right, I have one and they're summed. Rather than have two resistors here, it's one and they're in parallel, right? And then I can go on and make this R4 plus the parallel combination of 5 and 6, right? And now I'm gonna just describe the next part. I'm not going to do it. Then I can combine these in parallel, right, and get one final circuit. And then I can combine these two in series, and then I can get the total current. All right. So that's how you can see how series and parallel can be used to simplify things. All right. However, there's even for some things where there's only one loop, there's an easier way. All right. Okay. And I'm going to give these node names. Now, recognizing that these elements are all in series greatly simplifies the analysis. So there's only one path through Vn, right? It's only one current path. So the current here, 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 and here are all the same. Okay. So now we can use something called Kirchhoff Voltage Law that basically you sum the sum of these, the net voltage around the loop is 0. And you basically you look at the minus or the plus sign, and that tells you. So remember when I had a current and then I had VR plus minus? So if the current is flowing this way, it develops a positive voltage drop that way. So even though this is going in a loop, right, the current is going that way, current is going that way, current is going that way. So I get VR1 plus minus, VR2 plus minus, VR3 plus minus. And now I can use Ohm's law on each of these to relate it to current, right? So VR1 equals I R1 VR2. All right. So let's sum the loop. Minus Vn plus VR1 plus VR2 plus VR3. Those sum to 0. Substitute each one of these relationships, right, and solve for current, right, and I get I equals Vn divided by the sum of these resistors, which if you had done it the circuit transform way, notice these are in series, sum them, make a circuit where you have the voltage in one resistor, it would come up to be the same. Yep, that's another way to put it, but yeah, we'll just leave it at that. All right. So now I have a relationship for the current, which now I can plug back in here. And so what's VR1? It's Vn R1 plus R2 plus R3 times R1. All right. And VR2 equals the same scaling and same with all right. Now this example is done in the notes, and we are recording this video. So you don't have to be scribbling down. But there's just one thing that I want to point out is that this node voltage V3, because it's node voltages, right, V3 are measured from 3 to ground, right? So if I had my voltmeter and that was the positive side of my voltmeter, and this was the negative side, VR3 equals the node voltage at 3 when measured to ground. But V2 is not equal to VR2, because if I put my voltmeter here, V2, what's missing is the fact that it's with respect to ground. When you just say V2, it means with respect to ground. So if then I put the negative side here, well, I'm getting VR and whatever the drop is here, summed with whatever the drop is at R3, right? But sometimes that's a bit of a gotcha, all right? But this voltage division equation, we're kind of going to use a lot. And all you really have to do is recognize that you have this in series, right? And then use this equation, which I'm going to generalize. Actually, it's generalized in the lab manual, so you'll have it there. And then let's see. There's just one thing I want to talk about before we break out, is in the project, you're going to bias an LED to show that it, all right. And whereas before, in the other examples, I gave you the voltage and the resistors, and then you calculated the current and voltage drops, all right. Now, we're actually going to do a bit of design where I'm going to give you VN, and then I'm going to give you an IV pair, okay? And it's going to be 2 volts, 20 milliamps, all right? Now, the mesh analysis is still going to work even though the LED isn't linear, right? The current through a diode in forward bias is approximately equal to this, which is nonlinear. So you can't solve for things like you did when it was resistors, capacitors, and inductors. However, we can pull off a point ahead of time. We measure this and say, on this exponential curve, if I have 2 volts, I'm going to get 20 milliamps. So that's where it comes from. But how do we make it so that we're on that curve, right? Well, let's use our mesh. So minus Vn plus V our bias plus V LED. All right. Now for Ohm's law, that's I our bias. This is going to be 2 volts, right? This is going to be 5 volts because we know that. But let's just let's rewrite it once. Vn minus I, and I'm just going to say R bias, oops, plus V LED equals 0. The current, we want it to be 20, so we know what it is. So we're going to solve for RB, and I'm just going to do that. And for this example, where we have 5 volts and a 20 milliamp 2 volt pair, 150 ohms, will make sure that that circuit is biased properly. And you need to do that because if you were to put 5 volts across an LED, so much current would flow that it would just burn out. All right. So the brighter the bulb, the more the current, the longer, the less time it's going to last. All right. And so as you notice, the manual is getting built as we speak. That's the last thing that I have. You might not get to all of that by tomorrow. All right. But at least you've had a different way of listening to the theory than just reading the lab manual. All right. Now, what you're going to notice different about the lab manual today is I'm going to assume that you know things about LT Spice. So I'm not going to show you every mouse click, right? And as it goes farther and farther along, you'll kind of see, I'll go there, right? I'll say something like, build this circuit. Now, yeah, you might not know how to do that, so I'll have one thing, how to set that LED, right? But eventually, you're going to have to do more and more on your own, all right? But with all of this, we have enough so that we can now go test things, and we can test voltage division and whether our LED is properly biased with our kit, right? So that we're getting closer and closer to the ultimate circuit. Oh, biased. I'm sorry. No, I just thought like I'm biased. Like I don't like that resistor. But that's a great question. Okay. So to bias something is to set a DC voltage and current. So I wanted, in this circuit, I wanted 20 milliamps flowing through the whole circuit, and I wanted 2 volts to fall across here when the power supply was 5 volts. So the R resistance that makes that happen is 150 ohms. Okay, great question. Expected or designed? I want that bias to be that. But I think that's a good synonym. All right, so you should have received an email with a breakout session for not a breakout session, but a totally independent Zoom session for each TA. All right, that way, and the reason why is even though we can assign breakout sessions ahead of time, reading through the documentation, you had to have an account, and some people might be logging in not with their SJSU credentials, and so it would cause more trouble than it's worth. So I created all these 4 sessions, and so when we're done here, you'll log out of this session completely and then join the other session. And I set it for 2 hours every day until Thursday, not the weekend. All right. Now are there any questions? Sorry. Are there any questions about the theory bit? Okay. So what I'm going to do is stop recording so that essentially I can post the lecture. And then if anybody has any administrative type questions, we can do that.